All right. Welcome to our next session, everyone. Good to have you here, and good to have you here for this last day of our 2021 Goddard Symposium. We're really excited about this day. If you've been with us, day one, we were looking in, taking a good, careful look at how we're looking at Earth and what we're learning about it from, all of our different space-based data gathering and research platforms. Day two, we kind of looked around a little bit more. We looked at the moon, we looked a little bit further out at Mars, things like that, basically our solar system. Today, we're gonna look further out. We're gonna, set our sights to the distant reaches of what we can do. Both from a human exploration standpoint and robotics and autonomous systems. So to get started with that, let's get started with our next session. This one is called Deep Space Science, Humans and Robots Exploring Together. The US is entering a new era of deep space human exploration that will enable new scientific discoveries across a range of disciplines, taking advantage of different destinations, the microgravity environment, and distance from Earth. From studying celestial bodies to using them as research bases, this panel will discuss how robots and humans will explore together and the range of research that can take place when humans leave low Earth orbit behind. Our moderator for this session is Joel Kearns, Deputy Associate Administrator for Exploration at NASA's Science Mission Directorate. Joel, take it away, please. Joel?
Okay.
Here he comes. Turn on your video.
Thank you.
He's working on it. There he is. All right.
Thank you very much, Jim. Good morning, everybody. We have three great panelists today to talk about as we move beyond a low Earth orbit with humans as researchers and operators, how we're going to work together with our instruments and our robots and our teleoperated machinery to do scientific and technological research far from Earth. I'd like to start with Professor Clive Neal from the College of Engineering at the University of Notre Dame to give us an overview, particularly of lunar science that'll come up as we leave low Earth orbit. Clive?
Okay, thank you. You've got my slides. I just want to correct, I'm not a professor of lunar geography, as it said in the intro slide there, lunar geology. I thought I got another qualification that I'd forgotten about, but no, I checked. So I want to give a brief overview about science of the moon, because the moon is not just a place to learn how to go to Mars. I've heard a lot of talk, especially from NASA, about, well, we're going to the moon in order to learn how to go to Mars. But you've got to remember that the moon has a lot to offer in terms of not only lunar science, but solar system science, and maybe even beyond the solar system. And if you can look at the National Academies and Analysis Group documents that have come out, including decadal surveys, you can see that there's been a lot written about the scientific potential of actually having human permanence on the moon, especially with the beginning of that with the Artemis 3 Science Definition Team report, and what it can offer in terms of advancing science. And you can see down in the bottom there the main subjects that have been highlighted in a lot of these documents, and a lot more, I might add. But you can see, for example, the moon is certainly important for understanding how planets initially form and differentiate by understanding the interior structure and composition. And the moon is probably preserved that initial stage, which has long since been destroyed on this planet through plate tectonics, which is not present on the moon. But then also, what about the bombardment history of the inner solar system? And that's recorded on the moon, and that has implication for the origin of life on this planet. But I want to highlight the bottom right there, the lunar volatile cycle, just to sort of briefly, if we can go to the next slide, please. Because this is something that the more we sort of study the moon, the more it surprises us. So you can see on the left two diagrams there. In the late 1990s, Lunar Prospector showed the potential for actually having hydrogen deposits at the polar regions, presumably in the permanently shadowed regions, which was then confirmed with the LRO data, and there's the LEND neutron data, but there's also other instruments have now shown the presence of surface water ice in some of these permanently shadowed regions, but also at depth. And then the sort of I would say the pivotal moment, at least in my lifetime, is when samples brought back in 1972 were shown in 2008 to contain water. Definitive evidence, because we now had the technology to actually analyze these samples. And this caused a massive paradigm shift that the moon could actually have a water or a volatile cycle. And is what we see in the permanently shadowed regions actually the result of outgassing and cold trapping from these volcanic deposits? And because we found these signatures in those glasses, you then look at the M-cube data in the far right diagram, and you can actually start to see these hydration signatures in these regional pyroclastic deposits, these volcanic glasses on the moon. So this was a paradigm shift. Go to the next slide, please. And there's been a lot of talk about next slide. There we go. A lot of talk about the lunar resources because of these volatiles, and we have to be careful here because I think people are using resources when they actually mean reserves. A bit of geological speak there. Reserves mean that we know what's there, we know how much, we know we can extract it, and we can extract it at a profit, i.e. it's economically viable. And so we actually need a resource prospecting mission on the moon, and the Viper rover is the first step in that mission. But I'm sorry, we need a resource prospecting campaign, which is certainly more than a mission, but Viper starts that. But there's been a lot of blowback in some quarters saying, well, we need to do the science of these deposits first, otherwise they get destroyed. Well, I'd have to say I disagree with that viewpoint, and I think that we can go forward together. And the diagram on the right shows the synergies between science, exploration, and commerce in studying these volatile resources, because the data we get from prospecting is going to inform all three of these constituencies. We'll get a lot of good data about the science, the composition, understanding whether these contain the building blocks of life that were delivered to Earth. We will get that from, if we scale this prospecting campaign in such a way that we can get the data that's needed from all of these constituencies, everybody wins. So I think we can go forward together. Next slide, please. And that's my last slide, and then I'll be quiet. So the other issue I want to bring up is, because something that's really close to my heart is sample return. We've been orbiting the moon now. We have a lot of data from orbit, and we have a lot of data from the Apollo, lunar, and lunar meteorite sample collections. And we actually now know where we can have targeted sample return. So yes, we may be having a base camp, but there are things around the moon and places around the moon that contain samples that either are different from what we have in the collection, or simply we have no representation of them in the collection at all. And we know this now from orbit. And I just put these two little maps up that I constructed based upon the orbital data of these scientific opportunities for sample return, as well as resource prospecting around the moon. And I say the potential for science that will inform exploration and commercial activities is huge, and it's something that we shouldn't ignore. Thank you very much.
Thank you, Clive. I'm going to say a few words to start as a moderator about some of the implementation plans and the near-term activities and the infrastructure that's going to be related to doing research beyond low Earth orbit. Could you bring up my charts, please? Thank you. So for the cover, I just want to point out what people I think are thinking about a lot is going to be they naturally think about the first crewed Artemis landing mission, which is shown here in a NASA notional depiction from several years ago. And you can see here a notional lander with 2 crew members on the surface. The way you can see from the location of the Earth, it's assumed the landing is at a pole. I take it at the South Pole, which is NASA's destination. And you can see that there are large shadowed areas. They might be permanently or intermittently shadowed areas in the illustration. And you don't see much else there except for some lighting and a flag. And of course, what this depiction really doesn't show is what the likely situation is going to be with scientific apparatus or equipment that could be deployed, or perhaps there could be, much as we saw in the Apollo era, when Apollo 12 visited a surveyor landing site to look at previous robotic equipment, which had been sent to the moon to gather information, that we could see things like that in landing sites of interest. But before we get to the first Artemis crewed mission, I want to talk about some earlier activities which will be going on. If you go to the next chart, please. So NASA has implemented a method of delivering packages of equipment and scientific and technological instrumentation of the moon called commercial lunar payload services, where NASA is contracting to firms in the United States to land NASA equipment on the moon for NASA, but NASA does not own those landers or own the deliveries, does not own the mission that's going to be carried out by the commercial provider. And we have a cadre of competitively selected 14 organizations that NASA can then go to get bids to do a very particular delivering service, say that would go to a particular location or carry particular equipment, which could be scientific instruments, or it could be technological demonstrations, or it could be ways to gather data specifically for human exploration. And NASA has already made 6 competitive assignments from that group to deliveries, one of which is the one Professor Neal talked about, which is the Viper rover. But there are several others. There are 2 at equatorial regions, actually 3 at equatorial regions already selected, 3 at the South Pole region, and there's going to be 2 others that will be selected in the near future, which are again a combination of scientific investigations as well as technological demonstrations. They'll be selected soon. You can see from this map that depicts the landing locations and the notional dates that we've targeted dates in 2021, 22, 23, 24 for the first sets of missions, and that we expect, what you may not know is we expect to have a cadence of at least 2 missions per year that we'll select and schedule to land on the lunar surface, again, to do these scientific or technological missions. And you can see for these 6 deliveries, there are 4 industrial firms that are working to make those deliveries happen. 2 of the firms won 2 deliveries, 2 won a single delivery so far. And that the notional target, at least for the first deliveries, is the end of this year. Now, if you read in the media about a week or so ago, you'll see that one of the deliveries has been put off to early in 2022 due to launch vehicle availability. But we should be expecting to see scientific and technological investigations on the moon as early as the end of this year. If you go to the next chart, please. One of those, as Professor Neal pointed out, is Viper, which is a rover built by NASA, but again, delivered by one of these delivery providers that will explore the South Pole of the moon in search of water ice and other potential resources. And it's equipped with 3 instruments plus a 1-meter drill. Next chart, please. Another that's not shown as landing on the surface because it'll be in orbit is a small satellite called Lunar Trailblazer, a CubeSat-sized satellite, which is going to measure the form, abundance, and distribution of water, and both ice and hydroxyl groups on minerals on the sunlit moon as a function of location, surface, and soil maturity. It'll be able to distinguish the form, abundance, and distribution of these volatiles in permanently shadowed regions, and relate water abundance to factors such as fine-scale temperature variation. You go to the next chart, please. Then in the cislunar vicinity, we will have an assembly platform, a staging base to get to the surface of the moon called Gateway. And already scientific investigations have been selected for the Gateway. The first one is called Hermes, Heliophysics Environment and Radiation Monitoring Experiment Suite, which will use the vantage point of the Gateway to do studies of the solar wind and characterize several other aspects related to space physics, heliophysics. This is a point where we're doing science from the moon as opposed to exactly science of the moon, but it's one of the things that going out beyond low Earth orbit will enable us to do. We'll be able to use the cislunar vantage point to do studies that would benefit from being a little further away from Earth. Next chart, please. As Professor Neal pointed out, NASA using the existing community advice, for example, from the decadal studies related to the moon and subsidiary road mapping or planning or advisory committee, things based on that, used a science definition team to lay out several science objectives for the Artemis crewed landing activities that are listed here. And again, you can see that some of these are science to be done on the moon or from the area of the moon, and some of the science to improve our understanding of the moon. And some of them are related to applications and enabling exploration itself as opposed strictly to scientific studies. Next chart, please. And indeed, the candidate elements of what would be done on, say, the first 1 to 2 actual Artemis landing missions have been laid out, and NASA is now currently working on the details of how to accomplish those on the missions, which are shown here. And they break into 3 main areas. One you consider, field geology, sample collection and return. Another is in situ and field science, and a third are experiments or instruments that will be deployed by the crew. If you could go to the next chart, please. And it's probably my last chart. So what I'd like to do now, having given you some of that context for what NASA is planning or what's going on right now in the near term, I want to go over to Dr. Barbara Cohen, who's senior scientist at Planetary Geology, Geophysics, and Geochemistry Lab at NASA's Goddard Space Flight Center in Greenbelt. Barbara.
Hi, everyone. Thanks for having me. As Jill mentioned, I'm Dr. Barbara Cohen at NASA Goddard Space Flight Center, and I wanted to tell you a couple other things that NASA is planning in terms of science and exploration working together to really get at some of these questions at the moon itself. Next slide, please. So yeah, Clive already said this, the moon is a hugely important scientific destination. And I'm just going to point you here to a number of documents that you can read with varying degrees of technical information or public information. But the science community has thought long and hard about what we want to do on the moon. And that's because we've had a lot of time to think about it since the Apollo missions. And we haven't had humans on the moon doing real field work and sample collection and deployed experiments and rovers landed experiments since that time. So even though NASA has done a couple cycles of planning for humans on the moon, the science community has really been refining and revisiting and documenting our needs for the moon that Clive laid out for you. And here are some of the documents that really lay some of those out for you. So I would definitely point you to some of these great documents to look for that science in depth if that's something that you're interested in, including the United States Lunar Exploration Roadmap, Advancing Science of the Moon. Those are league documents, the Lunar Exploration Analysis Group. The Scientific Context for Exploration of the Moon is a National Academies document, as is the Planetary Decadal Survey, Visions of Voyages, and the upcoming Planetary Science Decadal Survey. All of those really reiterate the importance of the science that we want to do at the moon. Next slide, please. So in addition to all of the cool things that Joel mentioned that we're doing in advance of humans going to the moon, I just wanted to mention another one, which is the Artemis 1 mission itself. When we send the big SLS to test it out and have our great rocket launch, we are also launching 13 secondary payloads on that big rocket. These are very, very small payloads. They're 6U CubeSats, so 10 by 20 by 30 centimeters. They're very, very small, and they are getting a ride into cislunar space, into the area between the Earth and the Moon. And so from there, they can test out all sorts of novel and interesting in-space propulsion to get them to various destinations. Some of them are going to asteroids like Neal Scout that you can see down there at the left. It's going to be using a pretty giant solar sail to take it to a near-Earth asteroid and be able to characterize those as potentially hazardous objects. Several of them are going to the moon itself to look for the volatiles. That's something that we're really excited for humans to be able to do at the South Pole. But we have some data there. We have some maps. Lunar Reconnaissance Orbiter has been our real workhorse. We've had some ground-based observations of those areas too, but some of those results are still a little ambiguous. Clive showed you that great intersection of science and exploration trying to understand those polar deposits. And so here are some incremental ways to get at some of those maps or characterization of those deposits in the surface and subsurface. So I'm the principal investigator for Lunar Flashlight. That's going to be an active laser experiment to illuminate some of those permanently shadowed craters at the lunar South Pole and see if there's any signature of superficial water ice or like water ice frost. And Luna Map is going to be going very, very close to the surface with a neutron detector looking for refined measurements of subsurface water ice of the kind that's been detected from orbit, but at bigger footprints. So look for those on the Artemis 1 launch. That's going to be very, very exciting to be putting several things into orbit at once around the moon and try to coordinate those observations, especially with the ones from Lunar Reconnaissance Orbiter. Next slide, please. And I just wanted to mention as well, I was a co-chair of the Artemis 3 science definition team that Joel already mentioned that tries to take all of those desires and science things that we want to do and lessons learned from Apollo and tries to put them into a notional program. What would the astronauts actually be doing as they land on the moon? How are we going to get the most science bang for our buck? Science, of course, isn't the only thing that we'll be doing these missions for, but there's clear science benefits to having humans on the moon, especially in the realm of field science and context. That's what humans really excel at that robots don't. I'll just mention too, I'm a member of the Mars rovers, and we get images that we have to base our interpretations on. There's no substitute for a human picking something up, moving it around, catching the lens off the facets, and really developing an understanding of where that fits in with the big geologic picture at the outcrop scale. So we're very excited for humans to be going to the moon and really working on some of these problems in earnest, getting us some great samples, some well-curated, well-selected, geologically relevant samples from sites that we have the field context for. That's one advantage that humans really have over robotic missions, even though I love robotic missions. And deploying some experiments that maybe we don't have the robotic dexterity to do. One of the things that the Apollo astronauts did is be able to dig into the regolith and emplace things like seismometers. And you've seen the issues that InSight has had on Mars with trying to dig deep and bury instruments. It's not easy for robots. It wasn't easy for the astronauts either, but it was definitely, they're more dexterous, they have more mass, and they have more agility. So those are things that we're really looking forward to. But in order to really maximize that scientific return, this report also recommends that we need a lot of mass returned to the Earth, delivered to the surface and returned to the Earth. Starship is really going to be great for that. We want tools for sample collection, volatile sample preservation. These are much more advanced than what we had with the Apollo sample collection tools and curation. In situ instrument development, this is something the Apollo astronauts didn't have. They had their eyes and their brain, which is like 90% of what we want, let's be honest. But we can augment that with having real-time chemical data, real-time multispectral data. Imagine a point and shoot instrument that gives you the chemical analysis of a rock in real time. That's a real-time decision-making tool that the Apollo astronauts didn't have, but we can provide that now. We need power sources for overnight survival. Our eclipse landers, I have an instrument on eclipse lander. I love them to bits, but I want these to go on for multiple nights. And we don't have those power sources right now, or at least in a cost range and a mass range where they're deployable in our regular robotic missions. And mobility, mobility, mobility. The more mobility we get, the larger areas we can explore, the more we can go back to areas when we have questions about them and our understanding. So rovers, ways to bring tools around, ways to allow the astronauts to explore further are really, really important to us. And I think that's all I have, and I'll be happy to interact with the panel.
Hey, thank you, Dr. Cohen. Now let me turn to Dr. Rachel Klima. She's Senior Staff Scientist and Section Supervisor for Surface Geology in the Planetary Exploration Group of the Johns Hopkins University Applied Physics Laboratory. Rachel?
All right, thank you so much for inviting me to join. And I don't have too many slides, so what I'm going to be talking about, one of the roles that I serve in right now is the Director of the Lunar Surface Innovation Consortium. And we are, even though my background is as a scientist, and actually I'm Deputy PI on the Lunar Trailblazer mission that was mentioned, what we are doing here is working with the Space Technology Mission Directorate to look at, oh, I have to turn my light back on. If you sit too still, the lights go off. In fact, I'll finish what I'm saying and then turn it back on for the panel. I apologize. Anyway, so we are working to really amplify the connections between NASA and the community, like in the diagram that Clive showed, where we have this intersection between commerce and commercial industry, nonprofit organizations, academic institutions, government organizations. We are trying to provide a conduit to talk about NASA's plans and to talk about the capabilities that exist in the broader community so that we can leverage all of those to really engage the nation and the world in this effort and make this an inclusive and accessible effort that everyone can really be a part of in some way. So if you want to go to the next slide, please. So we are working with as a part of the Lunar Surface Innovation Initiative, and this is a group that has, it's an initiative in Space Technology Mission Directorate that is really trying to look at how to strategically fund some of these infrastructure items that we need to build up capabilities to have a human presence that remains on the moon, or at least comes back and forth to the moon from the Gateway for the long term. So this is not about just getting down there and touching the moon. This is about building the communities, the investments, and the technologies to really have a working environment on the lunar surface at this base of the South Pole. And the LSII has right now focuses on 6 areas, technology areas. There's crossover between them, which we also discussed, but those areas are extreme access. So things like being able to get into the permanently shadowed regions, potentially things like lava tubes, although at the South Pole, it's really the PSRs and doing things where we have to work with telerobotics or other advanced navigation. Lunar dust mitigation, of course, is a huge area when we're going to be having long-term technical elements operating on the surface and getting potentially gummed up by repeated landings, by dust being lofted. Also, for human health hazards, we're more in the kind of technical, what's going to gum up your machines area, but we want to interface with the human mission directorate to really talk about or to make sure that we are serving their needs as well with human health and whatnot. Extreme environments, we are going to have not only the extreme temperature variability that we know between like illuminated moon and dark moon, but as we build up infrastructure at the South Pole, we're going to be creating our own extreme environments by shadowing things and creating micro cold traps of our own. So that's what that group talks about, among other things, many other things, radiation, etc. Sustainable power or surface power, really. So, how do we build up a power infrastructure? How do we build up power sources that may be from different sources, like maybe nuclear, solar? How do we interface these together? What are the concerns for building, storing, distributing power? Those kind of things. In situ resource utilization, of course, is a huge one. It's kind of self-explanatory, right? We are going to have demos to show that we can either do water extraction or producing oxygen from regolith. And then, of course, surface excavation and construction, which is self-explanatory. So what we do is in the consortium, we have ongoing meetings every month that are open to the community. And we're trying to get these dialogues going on and looking at what we know of NASA's plans, what we know of the capabilities, and identify the gaps where we really need space tech to invest in order to advance these and move us to where we want to be ultimately in the next 5 or 10 years. So if you want to go to the next slide. I probably said most of this in words, but basically so the LSII is looking at all these technologies. The LSIC is reaching out to different communities and trying to figure out what technical expertise they have, what things have already been developed for other purposes that we could leverage for this effort. And again, it's really about bringing more people on board. And it's not that, NASA is doing something with a handful of researchers in kind of a black box. We want to engage the community across the whole United States and through, through different aspects, whether it's academia, nonprofits, government, or industry, and really get people bought into this and the importance of it. So if you want to go to the next slide, please. As we all know, and by having this infrastructure built at the South Pole, we're retiring all kinds of questions for moving further beyond Earth. We want this infrastructure there, and there's so much science to be done. In my dreams, I imagine something like the Antarctic Base, where we've got all kinds of ongoing science questions that we can ask. The moon is not a been there, done that at all. And especially when we get to the South Pole and we have those volatile traps where, we may have billions of year old records. We definitely have billions of year old records of volatiles that have come to the Earth moon system. And we will I don't think any of us can even imagine what kind of discoveries we will have, that we will make once we have access to those with both humans and robots that can access them, collect them carefully, bring them back, and really analyze things on Earth. So of course I moved into science. Go ahead to the next slide. So I just want to again reiterate, next slide, please, sorry. Just what Clive said back at the beginning, we're going to learn about the bombardment history of the solar system, our area, the Earth moon system. We'll learn so much more about how planets form. The moon is this Rosetta Stone for the entire solar system, and how we understand the solar system and how planets work and how life got to Earth and whatnot. So there's so much to be done. I'm super excited, and I will stop so you can ask some questions and I can turn my light on my office back on.
Thank you, Dr. Klima. I have a couple of questions that I'd like to ask the panel members, and I'm posing these to all the members, and I just ask that that you answer the ones that you like to answer. So my first question is, what research questions about the moon do you expect to be addressed, particularly in work on the lunar surface, that you expect to be addressed by teleoperated or automated robotic systems as opposed to astronauts actually on the surface? Or are there different types of investigations that you think would do one or the other, or there would be a mixture of both?
This is Barbara. I think it's definitely a mixture of both. Humans working on the surface and robots working on the surface are definitely complementary. They're good at different things. Robots can go long distances. They can go into really inhospitable territory. When we talk about those permanently shadowed regions, those are as cold as the surface of Pluto. They're 30, 35 Kelvin, 35 degrees above absolute zero. It's going to be very difficult to envision protecting a human body to the degree that they can go into those areas for any real length of time and do work. Those are definitely jobs for robots. That's what we do on the Earth. We send our robots into inhospitable places like deep seas and mines and things like that. So robots definitely have a job to do in science. Robots are also really good at exploring long distances. They can definitely do sample return. We can do a lot with sample return from robotic missions. But humans, like I said, really excel when they are giving us the geologic context, going back over ground, really getting at nuanced geologic field questions that require a lot of teasing apart and maybe going out and looking at outcrops again and again. That's not something robots are super great at. And also, of course, humans have their brains and their eyes, which are two of the most powerful instruments we can think of. There's a lot of processing power in the human eye and brain that they bring to it. And so they do it in a much more intuitive way and a much faster way to be able to cover that ground.
Okay. Any other comments from the panel?
Want to go first, Clive? I think we both unmuted.
All right. Just to say that a robotic prospecting campaign for the volatile resources on the moon. Repetitive measurements in a grid pattern. You don't want to send the humans doing that. We really need to look at that sort of use of robots to get those measurements, to understand if we have reserves of resources and if they're economically viable. And to me, that's the critical thing, because it will inform science, it will inform exploration, and it will inform commercial interests and, I'd put it bluntly, jobs.
Yeah, the only other thing I would add to that is that for things like large networks, robotics, sending things out, like we've wanted to do a geophysical network for a long time. A lot of these things, you don't need to send a person to every single spot. But if we want to look at kind of systems, global systems level items, the robotics is really still kind of our best path. And the other thing that's cool with things like the prospecting is that you can involve so many more people too. If you do telerobotics, look at the people operating the Mars rovers for decades now. It's such a huge way to get people engaged, from students and really join in this joy of exploration. It's really cool.
Yeah, and coupling telerobotics with augmented reality or virtual reality, that really opens up human exploration to all humans. That brings it back to us. All humans can participate, not just the few who are actually walking on the surface. And that's something that we can and should be doing on the moon.
Let me ask a follow-up to that. Now, as I mentioned, NASA plans to have a staging point in Lunar Space Gateway, which we envision as being kind of the central jumping off point. Jim Bridenstine, the former administrator, used to call it the command module in Lunar Space, where we envision landers will be stationed at the gateway. They'll probably be reusable. Astronauts will come from Earth to the gateway. They can transfer to the landers. What do you see what do the panel members see as being the possibility, since there'll be astronauts at the gateway and astronauts on the surface, might there be teleoperated activities going on from gateway or from Earth that are in parallel and complementing the activities that the crews are doing on the surface while the crews are on the surface?
Yeah, sure. I mean, following up on the AR/VR, part of what you need to make a really good immersive environment is a lot of data coverage, a lot of imagery, a lot of topography, maybe some multispectral data, things like that. That's where exactly what Clive said, those are your systematic observations. You want to run around in a grid. That's where robots are really going to excel, and you can absolutely do those robotically teleoperated. I think the Gateway sometimes has a lag that's appropriate for sort of joysticking teleoperation, and sometimes in its orbit it's too far away to really do the joysticking method, right? I mean, if anyone's a gamer, you know that even a couple milliseconds of lag time can be a lot. And if you're up to sort of a second or two of lag time, that's really hard to joystick things around. But you can also think about a fusion. It doesn't have to be one or the other. We have robots that operate right now. The Mars robots operate on their own. We don't joystick those. We uplink sequences to them. So you could have a virtual environment that you've painted where you joystick a sequence in, see where you want the robots to go, see what you want to pick up, and then it can execute it on its own while you're too far away to be interacting. So there's a whole hybrid world out there of teleoperation, AR and VR that we can take advantage of.
Thank you. Anyone else want to comment on that? Okay. I think there are some questions coming in from the audience.
Okay.
Oh, go ahead. Go ahead.
Yeah, I just want to say that when there was a Gateway science workshop, Gateway was very good for astrophysics, heliophysics, space medicine, that sort of thing, but it's least useful for lunar science. And that's what came out of that. With the architecture announcements, the recent architecture announcements, it would appear that Gateway's utility for enabling science on the moon has been diminished even more, but I'm waiting to see the ramifications of that. But having a regular access of humans to the surface, a regular cadence, so we can achieve sustainable lunar surface exploration with humans, is incredibly enabling for science. And if that can be done through Gateway, then it can enable science that way. But there are now on the table other options to do that. And that is a way to reduce the risk then, because you're not reliant on one portal.
Dr. Klima, do you have any comments before we move on to the next question?
Let's go for the next one.
Okay. Now, I think we have questions coming in from the audience that we'll get to, but before we go to that, I wanted to ask a question about science a little further away. We just the past few months have seen the great advancements of the landing and the initial operations of the Perseverance rover on Mars. So I want to ask the panel a question that's way beyond low Earth orbit, which is, how do you think astronauts will perform scientific research when they're at very long distances from Earth? For example, when they're orbiting Mars or on the surface of the Mars, or they're visiting an asteroid that's very far from the Earth. How do you think that will be different from what you anticipate being done as we explore the lunar surface over this next decade through Artemis?
Well, yeah, I mean, one thing is what you just said, which is they're very far away, which means a really long distance light time, which means you can't have real-time science backroom looking over their shoulder, making real-time decisions. In that case, it's even more important that you have a well-trained crew, that you just define the science objectives that you really want to do, and that you trust your crew. We have to build up that trust between the crew and the scientists and the mission operators to enable them to work independently. That's something that we can start doing on the moon as we build up our capabilities on the lunar surface. You know, one of the great things is that we can be looking over their shoulder and we can be making joint decisions. Bringing all that brain power to decisions on the moon is really powerful, But we can also be testing it in a mode more like an asteroid or more like Mars, where the crew can sort of get on the same page of what they want to do on an EVA, but then they execute the EVA on their own and come back and show the the mission operations and the scientists their results. We can test that. We can refine that. That's one of the great things about being on the moon is you can test out all of those operational ways of doing business. And get at really what you said. What do we need to make those things happen?
I just want to add to that astronaut training is critical, and there needs to be investments made in astronaut training so that opportunities are not missed or misused, because going to the moon is expensive. Going to Mars is hellaciously expensive, and we need to maximize those opportunities as much as we can. So astronaut training, the human mind and cognition is good, but a trained human mind and the cognition there on the surface of whether it be the moon or Mars is phenomenal, and and we've got history to show that.
Right, in geology. Not that we're biased as geologists, right? But but it's really understanding the rocks and not just seeing them all as little lumps of something, but to be able to critically analyze them and understand what you're doing on top of all the other astronaut training you need. The geology training is really going to be critical.
Okay, let me turn to Jim Way. And Jim, do we have audience questions?
We do. We have a couple. So yeah, this one's really interesting. So can the panel talk about the importance, and maybe this is for you, Joel, but can you talk about the importance of science return versus technology demonstration, especially with respect to the CLIPS missions? So and the other part of this question is the risk tolerance lower for missions with larger investments in the instrument, or roughly the same across all payloads? So I'll turn that to you, Joel.
Yeah, I would think every panel member can address, particularly the first question. There's a great mix of scientific investigations, technology demonstrations, and data gathering activities that'll take place on all the CLIPS landings that are planned so far, and I anticipate the ones into the future. The risk tolerance, I think, is different depending on how expensive and sophisticated the instruments are that'll be taken down to the surface. Although I would say for many types of instruments, we have deliberately, NASA has deliberately gone down to implement this CLIPS model, that we are buying a delivery service as a way to do a couple of things. We want to have the most efficient financial investment we can at the fastest cadence of delivery missions that we can. And that means that we are trying to tap into the creativity and the innovation of some of these newer entrepreneurial companies, as well as the more established aerospace companies, to make those deliveries on their own terms, to kind of be accountable for the success, to use the best of their engineering and technology practice, right? So that we will have a substantial number of these missions that are very successful. I think what's really interesting about CLIPS is the fast cadence of the delivery opportunities. And I think that as time has gone on, initially when the first CLIPS missions were put together, there was a real focus on the part of NASA to fly existing instruments or copies of instruments that had flown and could gather good data, good scientific data at the moon. But the key point was they had to be ready, because we wanted to be able to send them to the moon as early as the delivery opportunities could be made available by the suppliers. Now that there's a cadence of 2 a year, we've moved more to a cycle where we're doing solicitations, particularly for science, for the peer-reviewed investigators, where the investigators are building all their new instruments. Those will be taken down the surface of the moon. They're going to use that same model. But if we fly something really, really large down to the surface of the moon, there's probably a slightly less tolerance for risk, but we are still going to be using the same model on deliveries. Now, what I'm not commenting on is it's always possible in the future someone will propose a discovery or a new frontiers mission that will go to the surface of the moon. And I can't speculate that that would use the CLIPS model. That would probably be managed and executed under a different model with a different risk tolerance than what we're using for the CLIPS deliveries. Let me turn to the other panel members.
So the first CLIPS mission is a technology demonstration. This has never been done before, and it's been shown that soft landing on the moon is hard. We've had a couple of failures, but China's done it a couple of times now, and they've done a robotic sample return mission, so it can be done. The level of investment that's needed, maybe this is the level of investment that's needed to do that. We don't know, it's untested, but technological demonstrations are important to do because we have a valley of death in terms of technology readiness for instruments, because how do we get them to a point where they're beyond TRL-6 and up until TRL-9? Well, you can send them on a CLIPS mission to test them in situ. So I find this to be a fundamental way forward in getting new science data and creativity with new instrumentation to get us better data.
Yeah, I was going to say something similarly with, and now I'm worried that I lost the whole overarch of this. But you know, we will pick up great science many places. So you know, having these tech demonstrations and having a lower or a higher risk tolerance by the repeated opportunities, by the CLIPS model, I think is going to enable science we didn't expect to find. But I think also as we're building up infrastructure and testing the technologies, we need to keep in mind that having this, we're driving towards a place where we can do even more dynamic science. So it's kind of like the entire technology and science roadway kind of intertwines together and helps us evolve things on a pathway that will benefit both.
Yeah, Eclipse robotic sample return. We got lots of places where we could go with that. I mean, that is enabling. So hopefully Eclipse will evolve to something like that, because that to me is that changes. That really does change a lot of things. It's changed it already, but evolving it to doing something like that. And that's why I showed the maps. There's opportunity.
Jim, do you have any other questions?
Yeah, let's see. So this one, human space exploration beyond LEO has been largely couched in terms of going to the moon and Mars. Are there other compelling destinations for humans to visit in our solar system? And can the panelists talk about what kind of science humans could do there? And, you know, I think you kind of touched on this before a little bit, Barbara, but, you know, what needs to happen in order to make that possible?
Oh, well, I can't speak to what needs to happen to make that possible. That's a really complex question. But anywhere that we have questions about the geology, which is pretty much any solid surface. So pick your favorite solid surface. We've got questions on the geology. All of the planetary geology that we do is about how did that body form? Then we can try to understand what events went into forming it. What does that mean about how our solar system developed? And that gives us a context for where our Earth was in that history of the solar system. It all comes back to what we want to know about our Earth and our own evolution, and how do we place that into context. So if you were to explore Mercury, there's an amazing number of things on Mercury that we've learned through spacecraft that we really want to get to the surface. We want to get some samples and examine those. We want to understand the geologic context of some of those features, that would be awesome. What does it take to put people on Mercury? That is not my area of expertise. Or going to Europa, going to Enceladus, going to Titan, some of these really exciting outer planet satellites where there might be subsurface oceans and complex organic chemistry. Some of that is manifested on the surface as surface processes that reflect interior attributes of those moons. Some humans would do a bang-up job of characterizing that geology. What does it take to put a person on Titan? That's something that maybe a grad student thesis could be written on.
Anybody else? If not, I've got another question here. With Starship's large cargo capacity, and this one might be a little sensitive, but I'm going to ask it anyway. With Starship's large cargo capacity, it appears that Orion might become a bottleneck in returning samples. Is NASA looking at different means of getting samples collected on Artemis missions back to Earth?
Oh, this is Joel. I'll say that, you know, whether, no matter what system of the three that was originally being considered for this capability demonstration mission for humans to the lunar surface was considered, NASA was always looking at ways to get more samples back to Earth. You know, as I think Professor Neal talked about, the idea of having CLIPS eventually evolving to have a capability to get samples from the lunar surface back to Earth. That's not something that'd be done today. You know, that's a potential for the future. There could be ways potentially to bring samples from Gateway, a system back from Gateway to return to Earth. There could be augmentations to Orion in the future to get more mass back to Earth. There's a lot of possibilities. I would also caution people simply because NASA selected one particular provider that's got certain attributes for their vehicle for the demonstration mission. That doesn't mean it'll be the same provider for the missions after that. You know, Artemis, you know, if that's Artemis 3, Artemis 4, 5, 6, 7 could be done by one or more different service providers than the one that's originally doing the capability demonstration. So what we have to do is at least at this point, we have to plan. If you look at all these different likely ways that humans and their equipment can land on the moon and then get off the surface of the moon, we have to be somewhat agile and flexible and figure out multiple routes to get samples and equipment back.
Excellent, thanks. So I've got a couple of other kind of more different questions. This one's pretty cool. So there's been you know, discussion on and off a long time about space elevator. Is there feasibility of a space elevator between Gateway and the lunar surface?
Not with the orbit Gateway's in.
Okay.
That's I've heard ever since I've been studying the moon. I've heard about space elevator and how good it is, and I'm still seeing PowerPoints. So,
as I understand it, those space elevators have to go to a fixed point, like a geostationary point, or in the moon's case, you know, a selenostationary point. That and Gateway is not at that point. Gateway's in a different orbit.
So, just for my own clarity, how distant is that? Would a stationary point be from the lunar surface? You know, so that, you know, if this was even considerable, is there a distance, like a?
There is a distance. I don't know what it is. Yeah.
Is it the Lagrange point? Oh, okay.
It's a Lagrange point where you have no, but you've got to be stationary above the point on the surface.
Right.
So geostationary is like 23,000 kilometers or something like that above the Earth. So you'd scale it, I guess, for the moon's gravity, but I don't know what that number is.
Gotcha. Okay. All right. So this one actually, you know, we have just a few seconds left, but this is important because it's relative to students. If someone in high school today, what kind of education pathway would you recommend for them, to be looking at these missions, the robotics, and how the robots and humans will work together on future missions? Any tips there? Maybe Clive, start with you since.
Okay. Well, I actually teach a class in a College of Engineering called Living and Working on the Moon. And I'm teaching engineers, and I would say that you need to have an interdisciplinary education. Engineering is good, but you need to understand the environment, the location, the geology, the physics. So I would say an interdisciplinary education will open a lot of doors. Geology's opened a few for me, I must admit. But now it's teaching that next generation is really shown me how much interdisciplinary education is really valuable to understanding how you get the data back and how you actually get to the location and survive it.
Yeah, just to amplify what Clive is saying, I think when you're choosing your path in education, it seems like you keep getting asked to narrow, and you can get to the same endpoint a lot of different ways. And we look across the field, and we have people that came in through physics, through astronomy, through geology, through completely different things, through biology, through different types of engineering. And it's more about having the overarching curiosity and being able to absorb the kind of information from different sources, I think will really benefit you.
Thank you, panel members. I think that brings our session to a close. I want to thank you all for the preparations and the stimulating discussions and answers to the questions. Jim, I'm going to turn it back over to you.
Excellent. Thank you so much. Barbara, Rachel, Clive, really appreciate it. Joel, thank you so much. Great session. That was fantastic. Okay, so we're now going to take a break until 1 p.m. Eastern, except for the students. Thanks in part to our education sponsor, L3 Harris. They have the privilege of heading over now to a networking lounge where they're going to meet with and ask questions of both Dennis Andrusic and Thomas Zurbuchen. So that's super cool. Students, head over there now. It's down on the left menu. There's something called Networking Lounge. You click on that and in you go. Enjoy when you go in. Make sure your video is on, but keep your mic off and raise your hand if you have a question. So with that, we're in a break, except for the students, and come on back at 1 p.m. everybody else. Thank you so much.